So we have these quiz problems, 20% more than 40. Now, everybody got that rather quickly, but we write this out. We say 20% more than 40 is what? It's 40 plus 20% of 40. So that means it's 40 plus 0.20 times 40. And then that's easy to calculate. And you get 40 plus 8, which is 48. Everybody got that rather quickly. Okay, so what I'm asking people to do now is 20% more than the number 60. Write out a statement like 20% more than 60 is, or sorry, it's not 20% more than 60, 20% more than a number is. Okay, so like 20% more than a number is, but don't write 60, write a statement that tells you what it means to have 20% more than a number. And you're probably not real used to doing this, so that could be a little bit challenging. We'll see how everybody does here in a minute. Let's get the camera zoomed in because it just decided to go someplace else. Not as bad as it usually does. Okay. Trying to hit the pause button here. Okay, so it did pretty well. But as I said, it's kind of an art learning to put the right words in something so you can clarify your thinking and then do the math. All right, so. %20 more than a number is, I would say, that number is mimicking what we did here. We can't say 40, we don't know what the number is, right? So say 20% more than that number plus 20% of that number. That statement makes sense? Do you understand how that's a little bit of improvement over most of the statements that I saw, although some of them were pretty close? You got to say 20%. Well, you got to say whatever the number is plus 20% of the number, and referring back to that number does it. Now, I can take that statement a step further and say that put it up here. %20 more than n is n plus 20% of n. Okay, that makes sense? Instead of calling it that number, we'll just call the number n. And the meaning of that statement ought to be clear. That means whatever number we want to put in here, if we want to put in 40, we can do 20% more than 40. That would say 20% more than 40 is 40 plus 20% of 40. This statement will work anytime you're talking about some percent more than something, whether it's something you know, like here, 40, or something you're trying to find, like here, the number. Okay. Now, how would you write this as a mathematical statement? Kind of like 40 plus 0.20 times 40, but use n instead of 20. Can you write that out? Okay, now some people nailed it, and some people had a little trouble just figure out what to write out. I probably have figured it out by now, but we need to move on. And of course, you know, you're a distant student. If you weren't in class, you need to be working through this and doing the things that I asked before I show you. Okay, so what do we mean? this means N I'll give you a complete statement. So 20% more than N is N plus 0.20 times N. And you can put a multiplication sign in there if you want, but if you just write 0.20 N, it means 0.20 times N, right? Okay, so I didn't use the times sign like I did here. And I needed the times sign here or some indication of multiplication. So I just wrote 0.2040. That wouldn't make any sense. At least not in terms of the problem. Okay, so 20% more than N is N plus 0.20 N. Right? And that represents this part of the problem. So I'll outline that in green. I'll outline this in green. So we now know that this is N plus 0.20 times N. Now, how do you do the rest of the statement? It says 20% more than a number is 60, right? How would you write that? Could you write that as an equation? Okay, very good. Everybody got it. So now we can say it probably could be written as equation N plus 0.20 N equals 60. Now we can solve that equation, but before we do, we really want to talk about the distributive law. So we're going to go down to these equations here, then we'll come back to this, okay? Now I'm going to dispose of, well, I was going to dispose of it kind of quickly, but I guess maybe I better not. Okay, so take the equation 4x minus 3 equals 2x negative 2x plus 7. If you're doing it without making mistakes, it's okay to then write like -7 here, -7 here. I'd really rather see an equal sign there. -7 equals -7. Then we're adding one equation to the other. Okay. Now, if you're doing that right, okay. And if you're getting the right answers, okay. If not, I really prefer you don't write it that way. Okay. I advise you not to write it that way. I'm not going to count it wrong if you write it that way, but of course, if you make a mistake, you're stuck with a mistake. And some people, and the majority of people, even in pre-calculus, the majority will make mistakes by doing that. Now, it's possible to make mistakes doing what I'm going to show you, but I think it's less likely. Okay, so let's see. We want to subtract 7 from both sides. So I'm going to write 4x minus 3 equals -2x plus 7. And then I'm going to write down a -7 on this side and a -7 on this side. Subtracting 7 from both sides, keeping the equation in balance the way we saw with the weights on the meter stick last class. Okay. Now, what is it that we can subtract 7 from here? Can we subtract 7 from 2x?
She was right.
No, because we don't know what x is. 2x could be any number. Okay? This could be any old number at all. We can't subtract 7 from this unless we know what x is. And we don't know what x is. We can subtract 7 from 7. That's why we wrote it. Okay? So we get negative 2x here. Oops. Yeah, let's just be complete. That's negative 2x plus 0. You don't really have to write plus 0, but you have to understand 7 minus 7 is 0. That gives you negative 2x plus 0. And then we have negative 4x minus 3 minus 7. Again, we can't subtract the 7 from the 4x. We can't isolate the 4 and subtract 7 from 4 because 4 is multiplied by x. And we don't know what x is. So we don't know what number 4x stands for. So we can't subtract the number from something we don't know the value of. But we can do negative 3 minus 7, and that's going to give us 4x minus 10. Okay, now it's an unnecessary step to write the 0 there, but for now I'm going to write that just to make sure we understand. And, you know, for the upcoming assignment, I kind of recommend you write out that step instead of just crossing out the sentence. Okay. It's only a recommendation. But you're going to be better off, I think, if you do it that way. Okay. Now, usually we're going to get rid of the x's on the right side, get them over on the left, get the numbers over on the right. I wrote it in this order because I wanted to emphasize that we're subtracting the 7 from the 7, and we're subtracting the 7 from the negative 3. Next thing I want to do is get the x's over here where I've only got x's. Usually we get the x's on the left, but we can get them on the right. That's perfectly legitimate. So we have to subtract 4x from both sides. We do 4x minus 10 equals negative 2x. And then we subtract 4x. Well, 4x minus 4x is 0. And we have the negative 10. So we can write that as 0 minus 10. And negative 2x minus 4x, we can do that because it says whatever x is, we've got negative 2 of them here and negative 4 of them here. That's going to give us negative 6. So we have negative 6x. And then the 0 is really not needed there. So we have negative 10 equals negative 6x. Now we really kind of are used to thinking about it with the x on this side and the number on this side, but it doesn't make any difference. To get x is multiplied by negative 6. We can't add 6 and do anything with this. Because we add 6, we can't add 6 to negative 6x because we don't know what x is. Again, we don't know what the value of negative 6x is. So we can't add 6 to something we don't know the value of. So we okay. And what I just said doesn't get us anywhere, it just gets us back to something else we already had. So pretend I didn't say that. That would be legitimate. We could do that, but that's not what we want to do. That's talking about why we can't get rid of the 6 here by adding a 6 because this 6 is multiplied by x. Okay, what we want to do to get rid of this -6 is we write our -10 here, our -6x here, and we divide by -6. And if we divide -6 of something by -6, we just end up with that something. The -6 divides into the 6, gives us 1. So this gives us 1x on this side, and over 6 on this side. And it's not negative. If you're dividing a negative by a negative, that's going to give you positive. Well, now I'm going to reverse sides because you can always switch the two sides. 1x is just x, and 10/6 is 5/3. Now that we've solved it, we check. I take this solution and I plug it in for x here and plug it in for x here, which gives us 4 times 5/3 minus 3 equals, a little more space here, -2 times 5/3 plus 7. And well, this is the same as 4/1 times 5/3 minus 3 equals -2/1 times 5/3 plus 7. And we multiply numerators and multiply denominators, we get 20/3 minus 3 equals -10/3 plus 7. Now we can put the 3 and the 7 over common denominator and see if these add up correctly. We're going to get -1/3 there, and we're going to get 1/3 there. Means I might have made a mistake in my solution. Entirely possible. I was talking more than I was thinking. Let's see. We're going to do it differently, just so you can see one of the principles of equation solving you're going to need for one of the assignments it's going to be due, okay? We multiply both sides of this equation by 3. So first we write down the two sides. Leave ourselves a little bit of room. And we multiply both sides by 3. Notice that I put parentheses around everything that's being multiplied, and I've got to multiply the whole side. Now, when I multiply by 3, that means 3's got to multiply this, and 3's got to multiply this. Similarly, 3's got to multiply this, and 3's got to multiply this. So what we get is 3 okay, 3 multiplied by 20/3 minus 3 multiplied by 3. And that equals 3 multiplied by -10/3 plus 3 multiplied by 7. When I multiply this out, I get 3 times 20/3 Well, this 3 is going to divide this 3, and I guess I'd better write it out. So I'm going to just write it all in the same color. Since I'm multiplying this 3 by a fraction, I'm going to write it as 3/1 just to keep track of what I'm doing. And the same thing over here. You have a rule that says you can cancel this 3 with this. Okay. But the reason that rule works, and you don't necessarily have to write out the step I'm writing out, but I kind of think it's good if you understand it. This is the same as if I write 3/3 times 20/1, isn't it? Because when you multiply fractions, you multiply the numerators. 3 times 20 is the same here as it is here, right? And 1 times 3 is the same as 3 times 1. It's perfectly legitimate to do that. And then 3 divided by 3 is 1. And 1 times 20/1 is just 20. You divide 20 by 1, you get 20. You multiply that by 1, you get 20. So this becomes just 20. And then this is minus 9, obviously. And that's equal to what? Well, this could be written as 3/3 times negative 10/1 plus 21. Well, again, the 3 divides the 3, you got the 1, you got negative 10 plus 21, you get 11 equals 11. And now we've checked it. Now you're going to want to skip a lot of these steps, especially don't understand them. Your rule for cancellation. And I want to see anytime you cancel, I want you to write out why you canceled. Okay. And in this case, which is maybe a little, it's hard to understand, is this, you can get away with it because 3 is a factor of the numerator. It's a factor. It's one of the things you multiply to get the numerator. So 3 is one of the things you multiply to get the numerator when you do this. And 3 is also a factor of the denominator. Matter of fact, it's the whole denominator. So you take a factor of the numerator and divide by a factor of the denominator, and you can cross them out. If you say factor of numerator divided by factor of denominator, just factor of num divided by factor of denom. Okay. And I really kind of want to see you do that. Because people simply don't understand that when they come into these courses. Most people don't understand that, and it gets them in trouble in later courses. My pre-calculus students think you got a 2 here and you got a 2 over here, you can cross them out. Okay. Some of them, and nobody really would do that. But what I see in pre-calculus classes, people who come in a large portion, probably minority, but a good sized minority, don't understand the rules for cancellation, and almost everybody does it wrong at some point. You can't do it by the way it looks. You got to do it by the rules. And the rule is you divide a factor of the numerator by a factor of the denominator. Or if you add equal and opposite numbers, or subtract a number from the other. Subtract a number equal and opposite to another number. Subtract a number from the number, you're going to get 0. So that's a legitimate factor, or legitimate cancellation. Okay, so I don't want to go on too long about that, but there we have it. Okay, so this idea of multiplying both sides of the equation by your denominator or by a common denominator is really quite important. Okay. Want to move on to the second equation. When I said we have to multiply 3, when we have 3 multiplied by something in parentheses, if something in parentheses separated by plus or minus signs, then each of those things that's separated by plus or minus signs, call it term. Okay? Now that's standard terminology that kind of gets overlooked when we start teaching people to do math by habit. Okay? But this is a term and this is a term. This is a term and this is a term. When we multiply 3 by sum or difference of terms, we got to multiply 3 by every term. That makes sense? 3 is multiplied by everything, every term in here, everything that's separated by plus or minus from the other things. Okay? All right. So we're going to use that to solve this equation, and it actually comes out pretty easy. So what do we have? Let me back up a second. You always need to be writing out your check when you do a new assignment on a topic. Okay? And you really should be doing that throughout the course. Because if you always check, then you always know if you messed up. Or almost always. Sometimes you can accidentally make a mistake in the check that matches a mistake you made in the problem. And one time out of 100, maybe your check will seem to work, but it doesn't. Okay, anyhow, to the problem. We have the problem 2 times 3x minus 5 equals 4 times 2x plus 6. And I should read that as 2 times the quantity 3x minus 5 equals 4 times the quantity 2x plus 6. Say the quantity, you can say a little more than that sometimes. Okay, well, there it is. Okay, so what happens? Can you write out the next step here? In terms of what I did here. From this step and this step. It's very similar. Except we've got, well, we got some symbols, but that doesn't make a big difference. Now, if you're viewing the video for the first time, hopefully you've written out the step here that mimics the step I did from here to here. Now, what did I do here? And what did I say? Of course, you're not going to remember everything I say. It's coming at you fast, okay? But we had 3 times the quantity 20/3 minus 3. And I said, here's a term, here's a term. The 3 has to multiply this term, but because of parentheses, multiplying 3 by the whole thing, so 3 has to multiply this too. So what do we have to do up here? I don't also recommend that you necessarily skip the stuff I'm going to write at this point. Because, well, you got to multiply 2 by 3x, and you got to multiply 2 by 5. Okay, because 2 is multiplying each term in the parentheses. That's the rule. Okay, then 4 is multiplying 2x, and 4 is multiplying 6. And I can't forbid you, but I strongly urge you to write this step. Don't actually do the numbers until you've written this step and reinforced what it is you're doing. You're multiplying this by this, and you're multiplying this by this. Now, that's a pretty easy rule to get used to. After you practice it a few times, you'll get it. But if you're not writing out this step, later on, when you need it in a more complicated situation, you're more likely to get confused and stumble. So you stop yourself from stumbling later in the course if you take the time, just a few seconds, to write out this step. You also make it easier to check. So if you make it easier to find errors. If you check and find out that your check doesn't work, it helps to have this step to see where the next step comes from. And we have 6x then minus 10 equals 8x plus 24. And there we have it. At that point, we've got a problem just like the first one, and we solve it quickly. So I'm going to write down the steps. I'm going to skip a couple of steps. I'm going to do 6x minus 10 minus 24. No, sorry, minus 8x. I'll move the x's over here. Equals 8x plus 24 minus 8x. Okay. I subtract the x's from both sides. Because what that's going to do when I subtract 8x from this 8x, the 8x is going to go away, and then all my x's will be in this side. And then 6x minus 8x is negative 2x. We still have the minus 10, and that equals 24. And then negative 2x minus 10 plus 10 equals 24 plus 10. Once more, if you're making errors by putting the thing you're subtracting down on another line and then doing it, I want it written out on one line. Okay? Not that I'm going to count it wrong if you get it right. You're just less likely to get it right and you're less likely to understand it. Okay? So unless you're doing that right, if you've ever made a mistake by doing the two-line thing and you don't see me doing it, don't do it. Okay. In any case, we get negative 2x equals 34. X equals, well, negative 2x over negative 2 equals 34 over negative 2. X equals negative 17. Now, if I plug in negative 17, okay, I get 2 times 3 times negative 17 minus 5 equals 4 times 2 times negative 17 plus 6. How do I simplify this? Well, by the order of operations, I've got to multiply the 3 by the negative 17 first. So 2 times negative 17 is negative 34, 3 times negative 71, negative 51. Then I do what's in parentheses. I get 2 multiplied by negative 56 equals 4 multiplied by negative 28. The arithmetic is straightforward, but and that gives us negative 112 equals negative 112. And by darn, I did another one right. Okay. Don't skip this step. For the sake of what comes later, don't skip this step. And for the sake of getting immediate feedback when you make a mistake, which is a lot better than not knowing what mistake you made. Okay. You know, you put it into open math and it's wrong. What do? You just go on? Well, no, you check. Okay. And check it before open math tells you it's wrong. Of course, you're going to get the immediate feedback in open math also. But then work the problem out until you check it. If it's wrong, if open math says it's wrong, then you haven't checked. Okay. Then start checking. rework it and check. You learn more and you learn faster and you learn better. Okay. Here we go. So for the camera. Next time you have 3 assignments due, one of them is just doing what we've just done, using the distributive law. Okay. And also, you know, what you do when you have denominators. Open math's going to tell you everything I just told you. I'll tell you in a little bit different way. So just make sure you get it. I don't think you'll have any trouble from what I've seen here. A couple of things you needed to know. I think you'll pick them up. I think you'll be fine. There's a section on geometry that I might not talk about today, because I think you should pretty much know the areas of rectangles and parallelograms and circles, stuff like that. Stuff you've seen, stuff that's not too hard to understand. But then we'll probably talk about it some next time after I see how you do. Okay. But I want to continue talking about equations. Not all equations, excuse me, have numbers in them. Some of them have symbols. So let's take an equation like A equals 2W plus 2H. It's a formula for something that you really shouldn't need a formula for, but it's still kind of useful to have the formula and understand what it means. It's from geometry. It's a perimeter of a rectangle. And I said I wasn't going to talk about geometry. I just happened to do a geometry. It's just this: if you got a rectangle, and this is the width, and this is the height, and how far is it around? Well, whatever the width is, you got to go. If you're walking around it, you got to go W far here, and then you got to go W here, right? That's 2W. And then you also got to go up here and down here, which is 2H. Okay, simple formula from geometry. Okay, so perimeter is 2W plus 2H. We want to solve this equation for W. So what are we going to do to solve the equation for W? Is there something we can do? I'm going to do one thing just to make it a little easier for you to look at. I'm going to switch the sides. Since W, if we're going to want W to be on the left side, so we can end up with a W equals. So it doesn't have to be that way. It could be an equal something and then W, but we usually do it with the thing we're solving for on the left. Okay. Just like we usually get our X's on the left. So is there something I can do to both sides to get closer to having just W here? Okay, let me follow up with a question. Is there anything you see now on the left-hand side that you would, that can't be there if you're just going to have the W? And people said, well, H. Yep. What else would you not have? Oh, you don't want the twos. You just want plain old W, right? So what do? Well, usually we're going to look for something that we could add or subtract. And if not, then we look for something to multiply or divide. Okay. So ask what would we add or subtract? And somebody said, well, subtract the 2H's. Exactly what we do. We do 2W plus 2H equals P. We don't write anything underneath unless we're really secure to understand what we're doing. So this might be, not sure about the distance to you. everybody's doing homework in the distance is doing real well. So hopefully they understand as well. Okay, so we subtract 2h from both sides. Okay, I don't know about people in distance, of course, they're not doing anything. If they haven't done anything as of tomorrow, it won't be a course anymore. Okay, so we subtract 2h from both sides. Okay, well, what's 2h minus 2h? Can you show me with your hand? Zero, right? When you subtract something from itself, it gives you zero. Just effectively cancels it out. People like to use that word. Okay, so we've got 2w equals p minus 2h. Now what do we do? How are we going to get w? Okay, so what can we do to both sides to get closer to w? Well, we can get w. We can write, now normally we do this in one step, but we're going to do it in two steps. We write 2w, you know, we're going to divide, so we put the equal sign a little lower. And we have p minus 2h. If we divide both sides by 2, well, 2 is going to divide the 2, and we're going to get w equals p minus 2h over 2. So we just solved the equation for w. So now if I tell you, I've got this rectangular field, and I know that if I walk around it, it takes me 1,000 paces. And I know that the length of the field is 300 paces. Okay, well, what's that tell me? It tells me the perimeter is 1,000 paces. Okay. Well, let's say I know this dimension. Okay, let's say this dimension is 200. Okay. If I know P and H, then I can find how wide it is without having to pace it off. Now, if I've already paced all the way around it, you would think that I would be able to remember how long and how wide it is, but maybe not. Maybe I paced all 1,000 paces and didn't stop and think, well, how far did I go here? Okay. So what I do is I pace off this side, and now I know P and I know H. And now I can just do W is P minus 2H over 2. Okay. Okay, well, there's a little caveat there. I'm not going to bother to mention it. We're just going to leave it out. And so here's another one. I've got a circle. Its radius is R, and its circumference is 2 pi times R. Very common, fundamental geometric fact. Bad looking circle, but that is a good one. Okay, the circumference is 2 pi R. Circumference means how far I have to walk to go all the way around the circle. So I can write C equals 2 pi R. But if I've got a circular boundary or some circle, I can walk around it and see what the circumference is, right? It's a lot easier to do that than to try to figure out where the center of the circle is, so that I can pace off the radius. Okay. Not only that, but maybe that's a lake or something. I don't want to have to swim to locate the center. I could probably swim straight across it, and if I know how far I go in each stroke, then I could figure out the radius. It'd be half the diameter, so I could go all the way across, but of course I'd have to go at the right point. I wouldn't want to go across from here to here, or from here to here. I'd have to go across like from here to here, from here to here. I'd have to go through the center, and since I don't know where the center is, that might not be the best strategy. So I've got this circular lake. And I know the circumference. How am I going to find the radius? I don't see, how do I find R? Well, C equals 2 pi R is a perfectly good equation. So I write C equals 2 pi R. And then maybe I kind of target R, a little circle around R. That's what we're trying to isolate, right? So what could I do to get R by itself? Okay, so what do we do? Well, hint, you're listening student or somebody in this class watching this. There are no pluses or minuses anywhere here, so adding or subtracting isn't going to help. Like over here, we could subtract a 2h because it's added. Okay. Once we get down to 2w, we're down to multiplication or division to isolate w, so we divide by the 2. Okay, over here, one suggestion we got, okay, well, what would you multiply or divide by to get closer to having R by itself? I had a suggestion, well, divide by C. It's a legitimate step, but it takes us further from our goal of isolating R. Okay, if I divide by C, I get C over C, which is 1, but then I'd have to have 2 pi R divided by C. That's cluttering up the side that has R on it. Okay, so it's a legitimate step. It's a good suggestion, but it's not the one we're going to follow up on. So what we do is we divide by the 2 pi. So we do C divided by, and we do 2 pi R divided by, and we got to divide by the same thing. So we got to put the same thing here as we put here. Okay. So that gives us C over 2 pi. And if we're dividing 2 pi times R by 2 pi, the 2 pi will divide the 2 pi and leave us out. So just essentially one step. And maybe we want to say R equals C over 2 pi. As I said over here, usually say we're solving for what we want on the left. But that's trivial. We just switch the sides and it's still an equality. If that side of the balance is equal to this side of the balance, and that side is equal to this side, then if I switch them, they're still equal. Okay. Okay. So, okay, another formula from geometry. These actually make good examples. This is why I put the geometry right before them. Let's say this is L. Well, I guess we'll make this H. We'll take this W, we'll make this L, and we'll make this H. Then the area, total area, is two WH plus two WL plus two LH. And the reason for that is pretty simple. If you look at this face, the front face of the solid, we have we have an area, we have a rectangle with W line face. So if we multiply the two dimensions, W times H, that gives us the area of the front. The area of the back is the same as the area of the front, so we have two of them. If we look at the right face, its dimensions are L by H. So to get the area of the right face, we multiply L by H. But the area of the left face is the same as the area of the right face. We have two L. In the top and bottom, the bottom is W by L, so its area is W times L. And we got the bottom and the top that are equal, so we got two WL. So we're little geometry into this. So we can solve this. Let's solve that for L. Okay, what's the first thing we want to do in solving this for L? All the L's are on one side, right? We got L, and let's identify L. We got L here, and we have it here. Is there anything on the right side that we can get rid of easily? Okay, we would have probably add or subtract something, so we've got some additions here. And since all these are additions, we're probably going to subtract something. What could we subtract to get closer to isolating L? Well, think about it. Subtract two WH from both sides. That won't be on this side anymore. So we're going to subtract that. We're going to do A minus two WH equals two WL plus two LH. Oh, sorry, I didn't write that. That's what we're going to get. But I really should be writing that out. Okay, well, I've got two WH here and minus two WH here. So the two WH is going to go away on this side. We got A minus two WH equals two WL plus two LH. Now, after you, I'm not sure all that is visible, so let's look again. Okay. Again, we have what I said. A WH is the area of this face because it's W by H, and we have the front and back face with areas WH. We got two WH. The right face is L by H, so its area is LH, and the left face has the same area. That's also two LH. That's also LH. We got two LH. The bottom is W by L. Its area is WL. And the top has the same area, so we have two WL. Now we're solving for L. Okay, we look at this and look at what we can eliminate. So we say, okay, let's see, this thing doesn't have L in it. I kind of circled the L's to make sure I see where all the L's are, okay? This one doesn't have any, so I'm gonna get rid of it. To get rid of it, we gotta subtract it. So we subtract that from both sides. Get A minus two WH, and then we get this whole side, and then we'll minus two WH. Two WH minus two WH is a zero, subtracting something from itself. And here we have this. Now there's this step that I wish I had a little more time to explain, but I'm going to just tell you that this is equal to L times two W plus two H by the distributive law, because if I multiply through here, I'm going to get 2WL, and then I'm going to get 2LH. Okay, when the L is multiplied by both terms, I get back to what I had here. Now this is called factoring, and you're probably going to see that when we get to the section formulas. But it's a pretty simple factoring. It's just the distributive law. Okay, by the distributive law, this has to equal this. And I haven't changed this side. So there we have this. Well, now if I want to get L, I divide by 2W plus 2H. And of course, I got to do that on this side. And now I get L equals this. Now, fair warning, you can't cancel this H with this H because this H is not a factor of the denominator. It's not something that's multiplied through in the denominator. And this H is not a factor of the numerator. And this is where we really get into problems with canceling, because people want to cancel this H and cancel this W with this W and cancel all these twos. And it doesn't work. Okay. So that becomes a problem. So that's just fair warning. Okay. So we did manage to talk about both formulas and geometry in a way that I think is going to help you. Okay, well, good luck with the assignments. Run into, hang up, email me, let me know, and ask a good question. I'll be glad to answer it. And you won't have any trouble. It's okay. Can't take a lot of time to do this, but a couple of things. Number one, just a ballpark figure to make sure that we're in good shape. Okay, make sure we're getting something reasonable. Okay. Now, what we have is a 5-liter container full of monatomic gas, 300 Kelvin, 100 kilopascal. Gas constant is what it is. And well, you know, we get these two results from monatomic gas from kinetic theory. And just balls bouncing around in a container. And we developed most of that yesterday or Monday. Okay. So we get 20 joules per mole Kelvin here, 12 joules per mole Kelvin here. For the specific heat at constant pressure or at constant volume. Why is it higher at constant pressure than it is at constant volume? Because at constant pressure, the gas has to expand. And if it's expanding against its own pressure, so it's doing work. So you need more joules per mole Kelvin to do the work. Notice that this is, if R is about 8 joules per mole Kelvin, this is about 2.5, 5 halves of R, right? 5 halves of 8, half of 8 is 4, 5 times 4 is 20. Okay, and it's actually closer to 21 because it is 5 halves of this, ideally. This is 3 halves. Comes back to kinetic theory, so we're not going to talk about it right now. I'm just giving it to you, but that's a connection you're going to want to make. So you understand this better and hopefully eventually understand something about what an adiabatic expansion is. Eventually meaning like pretty soon. Okay, so anyhow, there's your information. Now we're going to heat this thing at constant volume till the pressure is 200 kilopascals. Then at constant pressure till the volume is 10 liters. Okay, at constant pressure, it has to expand. And they just heat it. So how much heat is required? Well, it's pretty straightforward actually, but let's do a few numbers. First of all, you know, hopefully you remember from chemistry or from reading or whatever, that you got about 22.4 moles, liters. Okay, a mole occupies about 22.4 liters at STP, standard temperature pressure. So how close are we to standard temperature pressure here? Well, standard pressure is atmospheric pressure, which is around 101.3 kilopascals. That's real close, right? Just round it to 100. And that's actually fairly accurate here at the altitude we are, about, you know, a little over 2,000 feet altitude. Relative to sea level. Standard temperature is freezing point of water, which is 273 Kelvin. So 300 Kelvin is pretty close. So we're within 10% of STP here. So we know that if we just use the fact that a mole occupies 22.4 liters at STP, we can figure out about how many moles we got in 5 liters. Okay, be about 5 over 22.4. You know, here's 5 liters, here's 22.4 liters. This is a mole, this is less than a mole. Turns out probably about 0.22 or 0.23 mole. Okay. So just take around 0.2 moles, just a ballpark. It's closer to 0.2 than it is to 0.3. We'll use 0.2. If it's 0.2 moles, then that means every Kelvin degree, we're going to use 0.2 of 20 joules, about 4 joules. Okay, 24.5 joules for every Kelvin. We're not going to do a temperature difference. I'm sorry. Yeah. We're going to raise this thing to 200 kilopascals. Now that means we're doubling the pressure, so we've got to double the temperature. Means we're going to have to raise it another 300 Kelvin. At 4 joules for every Kelvin, because that's what we get for 0.2 moles. We get 1200 joules. Okay, so again, to double the pressure, we got to double the temperature at constant volume. So I'm saying they're going, okay, we get around 1200 joules. Then we got to double the volume. Oh, I'm sorry, it isn't 1200 joules. This is a constant volume. Okay, it's 12 joules per mole Kelvin, which is about 2.5 joules per Kelvin at constant pressure. This would be a constant volume. This would be a constant pressure. Okay, so think about 2.5 for 300 Kelvin. That's about 750 joules. Then you're doubling the volume at constant pressure, which will cause you to have to double the temperature again. Temperature is already 600 Kelvin, so you're going to have to go up by 600 Kelvin now. You go up by 600 Kelvin at 4 joules per Kelvin. You got about 2400 joules, gives you about 3150. So ballpark 3000 joules if you do all the calculations. Okay, of course you want to do all the calculations. Do you understand how I'm thinking about this? Just we got about between 1/4 and 1/5 of the mole. So we're going to have between 1/4 and 1/5 of this and 1/4 and 1/5 of this. To double the pressure at constant volume, we have to double the temperature. And then at that constant pressure, to double the volume, we've got to again double the temperature. So we're going to end up at 1200 Kelvin. If you don't understand that, think it through. Just think it through, just in ballpark terms, because you have those numbers. Then you can work it out. Well, it's easy to work it out. I'm not going to work out the numbers. I'm saying that's around 0.22, 0.23 moles. Okay. It's between 1/5 and 1/4, and it's about halfway between. So I'm saying 0.22, I'd say 0.225, and then maybe a couple decimal places. A couple thousands over that. Okay. Anyhow, if you work this out, you're going to get this. So I'm not going to work out the numbers. Numbers are easy. Just plug them into your calculator. What's P? 100 kilopascals. When you start, what's the volume? 5 liters, which of course is 0.005 cubic meters. and you want to do that in cubic meters, so your units work. Okay, the pressure is in newtons per square meter, your volume would better be in meters. Okay, so you get Newton meters up here, which is of course the unit of work or energy. And that's significant, and we'll see that shortly. They just do RT. Okay, well, ours is about 8, T is about 300, so RT is about 2,400, but you got that 0.31, which makes it about 2,500. So you're dividing PV on RT, you get this. The numbers come out easily when you plug them in. So I do recommend you work things out in symbols before we go plugging numbers in. It gives you a better feel for the relationship. Okay. Now this could be figured at any state of the system. After you double the pressure, after you double the temperature, the volume, whatever. Okay. At every state of the system, we assume this is sealed. I didn't state that, but we assume it's sealed. So this doesn't change. So oh man, I'm thinking symbols here. What's a symbol for the molar specific heat? I think the standard symbol is C sub V, constant. Specific heat is often C. I use a capital C, V is a subscript, just a specific heat of constant volume. Then we can do a number there. 0.22 moles times 12 joules per mole Kelvin. Comes out about 2.5 joules per Kelvin. Constant pressure. You don't really have to do this intermediate step if you want numbers to think about. Doesn't hurt. Times volume first. Well, we don't know what delta T is, although we kind of do because it's a simple proportionality. So what's our delta T? Well, T equals nRT constant throughout. This is how I want to set this up. Less intuitively or rigorously, we can say do it like this. A constant volume is going to kind of skip a little bit there. It's a constant volume. if N is constant, and since it's a sealed container, the number of moles doesn't change. So N is constant, volume is constant, so we say P over T equals NR over V is constant. So you get one of those laws, Boyle's law, Charles' law, Billy Bob's law. Since this is constant, ratio of pressure to temperature is the same. It's one state as it is in another. So we get T2 over T1 is P2 over P1. P2 over P1 is 200 kilopascals over 100 kilopascals, which is 2. So T2 is going to be 600 Kelvin. That's how you can work it out very rigorously. Okay, pretty simple steps. Now I'm just trying to decide how symbolic I want to be. Okay. I've used subscript 1 for the original state, subscript 2 for the second state. Does that make sense? So when I say Q, delta Q1, 2, delta Q is the amount of heat that you got to add, okay? Between state 1 and state 2. And that equals your, well, this, so this is approximately 2.5 joules per Kelvin times 300 Kelvin, which is 750 joules. And of course, that's what I said fast originally. So there it is, a little slower, and there it is with some symbols. Okay. Okay, so from here, we're talking constant volume. A constant pressure. V over T, which is NR over P, is constant. It just turns out that the volume ratio here I chose was 2 because it's easy to work with. So the temperature ratio is 2. And T2 was 600 Kelvin. So we doubled that to get 1200 Kelvin. So the temperature change. I mean, the gotta add 2,400 joules. Let me digest that for a minute. And okay, so again, the question, what happens to pressure and volume as you go from state one to state two and from state two to state three? And it turned out was state one to state two, the volume stays constant, the pressure increases. State two to state three, the pressure stays the same, the volume increases. Okay. So what's happening is we start at state where the volume is 5 liters. So we put our 5 liters in. We put it here, so we got room to put 10 liters out here, right? It'd be a way to scale the graph. And our pressure is at 100 kilopascals, and it's going to double to 200. Okay, so in state one to state two, what's the graph going to look like? Well, the pressure is going to go from 100 to 200 kilopascals while the volume remains at 5 liters, right? So that means we're going to have a graph with a little arrow on it indicating that things are going in this direction, right? Okay. Then we go from 5 to 10 liters, and the pressure stays at 200 kilopascals. Well, there we have it. Okay. Now, how much work between state one and state two has the gas done? And if you say work by the gas, from state one to state two, from state two to state three. Well, why is it the gas is doing work? Because it's moving something in itself. Okay, well, go back to this example. If you increase the temperature and let water flow up the tube doesn't have much volume. And so we can kind of neglect the volume of the tube so that we heat this thing up, but the water doesn't move very far. So we say, well, the tube has very little volume. Any water that moves is going to move up the tube. Well, yeah, it does take a little work to get the water up the tube, but if to the extent that it's a thin tube, we can regard that as negligible. Now, if you're actually engineering a system, you're going to want to take that into consideration if you need that much precision, so you easily can. It's just minor complication. Okay, so right now we're just going to assume the tube has insignificant volume. This whole tube here has a volume of maybe 5 cubic centimeters. Okay, this jar has a volume of about 500. Okay, so that tube has a volume about 1/500th the volume of the jar. So if we fill the tube with water, we only, let's say 1/500th, 1/100th, 1%. If we fill the tube, we've only changed the volume of the air by maybe 1%. So we can kind of neglect any change in volume. Okay, so what happens is we heat the gas up. We do a negligible amount of work to raise the gas of the water. And nothing in here moves very much. So that the gas hasn't done much work. It hasn't lost much kinetic energy to the receding, the very slightly receding surface of the water. Talked about that last time with kinetic theory, okay? If your molecules are hitting something and coming toward them, they speed up. If they're hitting something that goes away from them, they're gonna lose kinetic energy, meaning their temperature will increase or decrease. Okay, accordingly, not much of that goes on while we fill the tube. So from state one to state two, ideally none. Gas doesn't encounter anything that moves. So there's no work because work is force times distance. It's exerting all kinds of force, but not through any distance, so there's no work. From state two to state three, gas does work. Okay. Now by a simple connection that I'll leave you to read about. Work is just P delta V. Work done by the gas. Okay, you can model that with a cylinder of any dimensions. Let the piston recede a little bit. Okay. Then that pressure is working against the receding piston. Working on the receding piston. For a small increment, you just multiply the pressure times the area of the piston to get the force, and then times the distance the piston moves, you get the work. Of course, now the pressure is a little bit less and so forth, and you got to set up an integral and all that stuff. But that's the simple stuff, okay, relatively simple stuff. So your work is P delta V. It comes down to what I just said. Wave my hands a little bit, but that's exactly what you do. Okay, so how is P delta V represented in this diagram? Well, there's free pressure. So, I mean, how would you show the amount of work on the diagram? How would you represent it on the diagram? That's where it happens. Okay, well, this is the pressure, this is the volume. The area of this rectangle represents the product of pressure times change in volume. And that works just fine, even if your pressure versus volume is a curve, because the area under the curve is just an interval. Generally, the work is the integral of the pressure with respect to volume. We just established it for a rectangular region. And since you can take any region and divide it up into approximately rectangular regions, do a Riemann sum, in other words. Okay. That extends to the interval. You just integrate pressure with respect to volume. So you want to store that away and try to understand why it's so. In terms of what I hope you learn in calculus. Okay. Well, how does this relate to the system we looked at in lab? Well, let's put some numbers on this, okay? I've got approximately 380. And that's just a number I pulled out, but actually, hold on. This does have milliliters marked on it. So I've got about 80 milliliters of water in about 0.93 of a half liter, which would be 465 minus 80. That comes out to 383. So my 380 is pretty good. Just don't block. Okay, so I got 380 milliliters there. I've got a question, so let's go ahead and see what the question is. A quick comment, somebody's a little bit disturbed by the fact that you got metal in there and not just water. Well, okay, to say this accurately, you have 80 milliliters of volume below the surface of the water, and there's very little metal sticking up above that surface. And that's actually the 3 milliliters that makes my 380 exact, so thank you. Okay, I hate to show off. Okay, well, now what did we do? Did the vertical tube, got water up to the top of the tube, should have gone higher theoretically at the temperatures that we were dealing with. So we didn't measure all that. We just got the idea, but we collected some water out of the top of the tube. Now, if I doubled the temperature, this thing's at 300, we get it up to 600. Okay, well, we can't really do that with boiling water. Yeah. You know, boiling water is at 100 Celsius, which is 373 Kelvin, right? So we can't even get it up to 400 Kelvin. So we'd have to heat it up with something else. Yeah, but maybe we use a blowtorch or something to heat that surface. We could heat it up. We wouldn't want to do it in the lab because we don't want to start a fire. There's a lot of flammable stuff around here, so we wouldn't do that. We wouldn't use an open flame. But we couldn't do it just by immersing this in boiling water. We could do it by putting it into superheated steam. Probably be hard on the lid here. So, but you can imagine you could make a 5-liter vessel out of a ceramic or a metal, seal it off, and use it to raise water. Okay. Or you somehow use that pressure to do work. Doesn't have to raise water. This is just an example of how you do work. You could, well, a number of things you can do. Assume you're going to be mechanical engineers. I'll come back and explain it to you. Okay. Because I'm not likely to come up with a refined system. But if you give me a refined system, I can probably do the physics of it. Okay, so this is, this is heating the stuff up. Now the next phase is we got to cool it back down so we can do it again. Okay. So what could we do to this thing? We heated it up, water got to the top, okay, of the tube, then water came out of the tube. This much work was done. Then we got to cool it off. Okay, so we got to complete this cycle, and there are different ways to cool it off. One way is open a valve and release the pressure all of a sudden. Okay. The curve here depends on the ratio of CV to CP to CV, CP over CV. It's around 1.4 for air and 1.6 for monatomic gases. We're not gonna talk about that right now. We might not get to talk much about that, as we have limited time. You could pull it off very gradually so that PV equals nRT applies throughout. And of course, it does apply throughout. You get different curves, but you can get a shape that looks like this, basically, with most ways of pulling it off. Okay. So you bring the pressure down while allowing the temperature to, you bring the temperature down while allowing the thing to expand one way or another, suddenly or slowly, isothermally, whatever. And then you just let the volume decrease. Now you could do it along any curve. You could do it like this. And you could think about what it means to do it like that. It turns out that the net work that you get from the process is the area under this curve. Okay, and there's the work you get out of your heat engine per cycle. Now you compare that with the energy you've got to put into it. What are you getting out of that 3,150 joules or 3,200 joules, whatever, okay? And it turns out that this is a lot less than that. Okay. What I want to do is I want to go on with the heat engine idea a little bit. So we're going to ask you is, okay, now how high is the water in the tube when you get here? Okay. So where are we collecting the water? At what altitude are we collecting the water? If we have double the pressure. So work on that for me. I'm going to clean the board. So we want to know what we want to know. Actually, we do it like this. Let's generalize this. We kind of a little bit of stuff. Here's V. Here's P. Here's our initial state. Okay. And here's our, actually, I'm going to call it V naught, P naught, because that's usually what we do. I started using 1 and 2 for the subscripts over here. We generally start the subscript with 0. Okay, so we have V naught, P naught. Now we have another state here. Okay. At this state, think of water in the container in a tube. Because it's really simple to think about that because we can really do that here. Okay. But this all generalizes to any. Okay. So the height is H. So what's the pressure here? Okay, so you got a real good quick answer there. You can get them off the board or anything. This state would be V naught rho GH. Okay. Now, what's the temperature? Well, that depends on what the temperature was here, right? We're gonna call that T0. So what's the temperature in state one? Still don't have everything. What's the expression for the temperature in state one? In terms of H and T0. Okay. So some of you are on the right track, but it's actually fairly simple. I hope I haven't thought it through. But the question is obvious and the answer is pretty simple. We know that from state 0 to 1, volume's constant, P over T is constant, right? You want to use that kind of reason. You use that again and again here. Well, P over T is constant. Well, there's your pressure. And I wrote rho GH here again. It would be P naught plus rho GH, right? Okay. Wrote that carelessly, but this is what it is. So the T1 is P naught plus rho GH over P naught times T naught, which just comes right out of this. In other words, your pressure goes up by factor P2 or P1 over P naught. So your temperature has to go up by the same factor. Okay, this is your ratio of pressures. There's your ratio, there's your original temperature. So that's pretty straightforward. Okay, well, now let's say that we go up to stage 2. The temperature equals T2. Well, what's the pressure in the volume? That would be the state of the system. I'm giving you a temperature. In other words, there's some maximum temperature that you can achieve with whatever it is you're heating it up with. Okay? Whatever you're heating the gas up with. So whatever that is, that's what it is. And now we can tell if we raise it a certain amount that we regard as a variable right now. Now, how much water can we get out of it? And how much work do we get? Okay. And we're not yet getting the work in a cycle, but we're getting the amount of potential energy, amount of mechanical work that we get out of this system. Okay. So what's P and T here? What's P and V? Then we're gonna reason just as we did here, or we can even reason very intuitively. Like we can probably reason out the ratio of the volumes without even going back to PV equals nRT, but it helps to go back to PV equals nRT to get used to doing that and to see where our proportionalities come from and to confirm the intuition. So to be rigorous, you gotta go back to PV equals nRT. What do we do over here? We said V is constant, and then we're on our way, right? What do we know from state one to state two? Let's do that. Okay, so dot, dot, dot. No, I write V two over V naught equals T two over T one, not because I'm comparing this state to this state, but because V naught is still the volume when you get to state two, right? So I could say V two over V one equals V two over V naught, because V one equals V naught, but that equals T two over T one. So the pressure is P two. And the temperature ratio is T two to T one, whatever T two is, assuming you know T one, which is T naught. And no, I'm sorry, T one is this. Okay. So, you know, T two over T one, and it's T two over T one times V two. So you can figure this out. So you can now figure out is P delta V equals whatever, etc. You got the work. Okay, now my question is, work all this out symbolically. Get your expression for the work, which you got all the pieces of. Okay. Excuse me, get your expression for the work. And that expression is going to be a function of H. Okay. So that if you're given T naught, V naught, and P naught, you know the state of the system. So what H maximizes W12. If you write out your expression for W12, and all the pieces are here, they can easily be put together. If you write out your expression for W12, how do you then figure out what H maximizes W12? What would you do with that expression?